What if there were devices that could solve problems in the blink of an eye? Problems that would take even the fastest supercomputers billions of years to solve. What if we had computers so powerful that they could simulate all of nature's processes and provide us with all the answers to the big questions of humanity, from the creation of the universe to the evolution of life? Well, then we would have arrived in the exciting world of quantum computing. Indeed, scientists at the famous University of Oxford have now achieved a groundbreaking milestone in this field, connecting two quantum computers for the first time to solve a highly complex quantum task together. In the course of this, a quantum logic gate was teleported over a distance of 2 meters. But how does something like this actually work? Why are quantum computers suspected of radically changing our daily lives in the future? And what actually gives them their incomparable computing power? It's a report that makes you sit up and take notice. A few weeks ago, the leaders of Google Quantum AI announced that their quantum processor, Willow, solved the task in just 5 minutes that would take the world's best supercomputer, believe it or not, 10 quadrillion years. That's a 1 followed by 25 zeros. But how is it that quantum computers turn even the most powerful computers of our time into lame snails? To understand this, we first have to visualize how our current everyday devices work in the first place. Whether you're watching this video on your laptop, cell phone, or tablet, all these devices work with bits, units of information that can only assume the state 1 or 0. In today's computers, the corresponding states are represented by electricity in the processor, where electricity on means 1 and electricity off means 0. As their name suggests, quantum computers, on the other hand, use quantum bits, or qubits for short. These can also assume the state 1 or 0. But they also have another remarkable ability that clearly distinguishes them from classical bits. A qubit can also be in the state 1 or 0 at the same time, or theoretically, in an infinite number of states in between. If we imagine a classic bit as a coin that either shows heads or tails, a qubit is a coin thrown into the air that spins around at a rapid pace. As a result, we cannot say which side is currently facing up because it is in both states at the same time. Ultimately, it's precisely this property of the qubit that makes a quantum computer many times more efficient than a conventional computer. It needs significantly fewer qubits than bits for the same calculation. In a conventional computer, 2 bits can only represent one number at a time. But as already mentioned, a qubit can assume an infinite number of different states simultaneously. Even if we only assume 2 different states at the same time, each additional qubit exponentially doubles the number of simultaneously representable states. While 3 qubits can already assume 8 states simultaneously, with 300 qubits, it's as many as 2 to the power of 300, a number greater than the number of particles in the universe. But that's not all. In addition, the qubits in a quantum computer can also be quantum entangled, which means they are coupled to each other. In colloquial terms, as soon as a qubit is brought into a certain state, the state of its entangled partner also changes at that moment. And mind you, at faster than light speed. This is the background to the fact that calculations in a quantum computer can also be carried out faster than the speed of light. But what does all this actually achieve? Or to put it another way, what practical uses do these wondrous devices actually have? Well, none at the moment. But as soon as the state of the art allows, scientists want to use supercomputing power to simulate the interactions of molecules or their possible states and thus achieve new breakthroughs in the field of drug development. AI could also take a giant leap forward with the help of quantum computers. The development of new materials and the fight against climate change could also benefit from the power of this futuristic technology. Yet, for the time being, we simply cannot foresee exactly how many applications quantum computing will have. Some experts even assume that we will use the computers to simulate all of nature's processes and thus finally crack the great secrets of the universe and answer the question of the origin of life. But why do qubits pose problems for researchers? All this, mind you, is only possible with the help of exotic computing and information units. But how is a quantum bit created in the first place? Experts have various options at their disposal to generate qubits. Google uses special quantum chips on which weak currents flow in circles in the smallest of spaces. Each circulating current represents a qubit and, similar to ions, can be brought into different states and read out with the help of microwave radiation. The aforementioned Willow quantum processor, for example, is equipped with 105 superconducting qubits. Aside from that, it's also possible to create qubits by trapping ions in magnetic and electric fields. Once trapped in this ion trap, they too can be brought into different states using microwave radiation and thus loaded with information, at least in theory. But the practical truth is that the field of quantum computing still faces some significant problems. After all, there's a reason why we're not all walking around with a quantum smartphone in our pocket. In order to manipulate and capture the moving particles of the qubits, they had to be immobilized by cooling them almost to absolute zero, minus 273.15 degrees Celsius. Furthermore, qubits are extremely sensitive, and any disturbance, no matter how small, destroys their quantum state. No matter how well the experts shield them from vibrations, magnetic and electric fields, and all other external influences, qubits only remain stable for fractions of a second. The corresponding calculations must therefore be completed in this very short period of time. For this to succeed, researchers must constantly increase the number of qubits working together. But this is easier said than done. Although quantum computers with 1,000 qubits made of ions or superconducting quantum dots already exist, researchers suspect that the quantum computers of the future will need millions of qubits to be truly practical. However, the more qubits a quantum computer has, the more unstable and error-prone it becomes, and experts have to resort to complex correction methods. In the case of Willow, for example, the scientists implemented a so-called surface code, which means that the quantum information is no longer stored in a single qubit but distributed across several physical qubits. Together, these form a logical qubit, or in other words, a computing unit. In this way, the necessary information is preserved even if a single physical qubit makes a mistake. But perhaps, and this is the exciting part, this scaling problem can also be avoided with the help of teleportation. How did Oxford scientists teleport a quantum operation? To avoid misunderstandings, it should be noted that quantum teleportation differs somewhat from the wondrous technologies presented to us in Star Trek and the like. While teleportation in science fiction refers to machines that can transport matter from one place to another at the push of a button, quantum teleportation merely describes the transfer of quantum information, such as the spin state of an atom, to a distant second atom. Now that all the ambiguities have hopefully been cleared up, we can turn to the exciting work of the Oxford scientists. In fact, David Lucas's team is using modular quantum computers for this purpose, with each module containing only a relatively small number of qubits. These are connected to each other via classical and quantum channels. While the individual quantum modules remain relatively stable in this way, they can execute larger quantum algorithms in combination. Indeed, Lucas and his team of experts recently succeeded in coupling qubit modules in such a way that they solve the quantum algorithm across modules. Each module consists of two qubits in the form of ions, a calcium ion, which acts as a circuit and additional qubit, and a strontium ion, which serves as a network qubit. The latter is connected to the network qubit of the second module via an optical fiber. The collective calculations begin with the network qubits of the modules becoming quantum entangled. Photons, which are coupled to one of the qubits, play the role of matchmakers. Once the entanglement is established, each module generates a so-called controlled Z quantum gate, CZ for short, between its network and circuit qubit. The experts explain that such a gate only reverses the sign of the digital 1 while the 0 remains unchanged. The trick here, however, is that the entanglement of the modules causes the quantum gate to be teleported. In other words, the qubit's operations in both modules effectively run in the same gate. This enabled the Oxford researchers to connect the separate quantum processes into a single, fully connected quantum computer. The quantum operations performed by the qubits in the modules only become complete with the exchange of quantum information between them. To prove that the modules really do compute with each other, the experts put the theory to the test and had the module computer execute the so-called Grover algorithm. This is used to track down a specific entry in an unsorted database, and the collective computer successfully solved the task. Although previous experiments in quantum teleportation had already exchanged quantum states between physically separate systems, this was the first time that an algorithm had been executed by a distributed quantum computer, and a real interaction between the separate modules had been generated. According to the scientists, what they have now demonstrated on a small scale could have laid the foundation for a great future. On the one hand, such distributed computing would pave the way for larger and more powerful quantum computers, and on the other hand, it could form the foundation of the future quantum internet. Now, with just one click, you can lay the foundation for your future subscription. Click subscribe now so you'll never miss a new video from us again. We'll see you soon.